right, so partial fraction example. What I generally try to do with this setup for the exam is really just focus on the topics that are most important moving into the next course. The next course could be differential equations or Calc 3, and these are the ones that are most useful. Although series convergence and divergence, maybe not as much in Calc 3, but or at least in the early goings. All right, so what we're doing again is we're pretending the integral isn't there. We're looking at this as just 2x cubed, x squared plus 3 over x times x minus 1 as a quantity squared. All right. So we have two unique linear factors on the bottom. So each one of those is going to get a constant numerator in the expansion. So I'm going to write this as a over x. Then plus, I'm going to get a new constant, a unique constant for the x minus 1 squared. But we got to bear in mind, because it's a power of 2 for that linear factor, we have to start off with the constant over the factor raised to the first power, and then a unique constant for the factor raised to the second power. All right. The idea being that if we got something like x minus 1 to the fourth, it would be b over x minus 1, c over x minus 1 squared, and d over x minus 1 to the third, and then you keep going e over x minus 1 to the fourth. All right, so not fun. I would never do that to you on a test, but it's conceivable, I guess, that it could happen at some point down the line. So we multiply through with the x times x minus 1 squared. When we do that on the left-hand side, it just boils down to a 2x cubed, it's squared, I keep saying cubed, plus 3. On the right, we would have a times x minus 1 squared plus b multiplied by x times x minus 1. One of the x minus 1s would cancel. And then c multiplied just by x. All right, and there's a bunch of different ways to handle partial fractions. The way I like to do it is to distribute everything out on the right-hand side and write our linear equations, or equations, not always linear. So this part, I'll just highlight it, or right here, is going to become x squared minus 2x plus 1. So I'm going to multiply that by an a. All right, so a x squared minus, all right, 2xa plus a plus bx squared minus bx plus cx. All right. The other technique involves you plugging in the roots for each of these factors. So if you plug in a 0, you get one equation across the board for x. If you plug in a 1, you get another equation, then you can solve that system. It's just not the way I like to do it. But if you see anything similar to that, or a tutor in the tutorial tells you to do something like that, then there is merit to it. It's just not the way I like to do it. All right. So I have ax squared and bx squared that somehow have to add to 2x squared, which means the a and b values have to add to equal 2. All right. There is no x value on the left-hand side, which means anything that has an x in it would have to add to 0. So we'd be looking at negative 2a minus b plus c would have to equal 0. And then anything that doesn't have an an x attached to it would have to add to the constant. So that's telling us that a has to be equal to the 3. All right, so you could use the calculator for this, but you could also, I mean, it's pretty much solved because they tell us, or we discovered, that the a value is equal to 3, which means the b value has to be equal to negative 1 if you're going to get to a 2. So then it really is just a matter of evaluating this one. Negative 2 times 3 minus negative 1 plus c would be equal to 0. So negative 6 plus 1 plus c equals 0. So c would have to be equal to 5. Is it? Yeah, but then you got to add it to the other side. Okay. All right, so we know A, B, and C. That's great. That's wonderful news. There's a lot of work to get there. Unfortunately, it does not mean that you're done with the problem, because we still have to integrate. But at least now I know what I'm integrating. All right, so it'd be, instead of a over x, it would be 3 over x. Instead of b over x minus 1, it would be negative 1 over x minus 1. And 5 over x minus 1 squared. All right. So I have to integrate. First two are going to be easy enough. First one's 3 times the natural log of x. The second one, I'll just carry this negative 1 out. Negative ln of x minus 1. But the last part, you might do a little u substitution, but since the derivative of the inner function is not anything other than 1, there really isn't anything to do. So what I'm going to do is I'm going to rewrite it as 5 times x minus 1 to the negative second and apply the reverse power rule. All right, so increase the exponent by 1, you get x minus 1 to the negative first. Divide by that new exponent, so it's really negative 5. And the only reason that works without u substitution is because the inner function, the x minus 1, has a derivative equal to 1. So you can differentiate or anti-differentiate around that inner function because the inner function doesn't play a role in the derivative, except to be part of it. Okay? So I can check this by differentiating. Negative 1 times negative 5 would be 5. X minus 1 to the negative second. But then multiply by the derivative on the inside. Derivative on the inside is equal to 1. It's not going to change anything, so I don't need to worry about it. And it's the same reason why I'm able to jump right to the natural log of x minus 1 from this, because that subtraction or addition on the bottom of a fraction doesn't impact the derivative of the function at all, because the inner function has a derivative equal to 1. All right. So that's definitely a pretty beefy example. A lot of stuff going on. In terms of the actual calculus of it, though, not that bad because it's all basic rule base. It wasn't like you had partial fractions and then within the partial fractions you had to do a trig substitution or integration by parts or something like that. Those are some beastly ones. I mean, I've seen some problems. I've had to do some problems when I was in your shoes where all that stuff was in one question. And there was 10 of them. I was like, how are we supposed to finish this? It's a challenge. Right? So that wasn't in the practice exam, so I figured I'd go over that. There wasn't a linear differential equation there also, either. Words, English. Appropriate form, and that's the big challenge. It should be in the form, a linear form. Once that happens, then we want to get our mu sub x, or mu of x, which is e to the integral of p of x dx. All right, so we have to kind of move some things around sometimes anyway. In this case, it's a very slight adjustment. I'm going to write it as t squared and then y prime as opposed to dy dt plus 3t times y equals all that fun stuff on the right hand side. All right. What defines something as being a linear differential equation is this structure. It's something multiplied by y prime, something else multiplied by y. All right. I mean, that's an oversimplification of it. There's more to it than that, but for our purposes in this course, before you start exploring this stuff in great detail in the differential equations course, we can just kind of live with that as a working definition. All right. So what we want to do is get it so that it's just the y prime to start off. So in order to do that, I have to divide out the t squared. All right, the p of x comes from your differential equation written in this form. All right, this guy right here is my p of x. All right, so if I want my mu of x, it's going to be e to the integral of, well, we're working with t's, right? So let me get rid of that x and make it a t. So it's not really p of x. I'll put it in p as quote x. It's really p of t. So 3 over t dt. All right. So that's e to the 3 ln of t. We don't worry about the plus c. That's all going to work its way into the final answer. Exponent jumps over to log like a frog. That's Hamilton would say. So we're looking at e to the ln of t cubed. All right. What that ends up being is just t cubed. All right, the e and the ln will cancel each other out. I'm also able to drop the absolute values. I kind of didn't have to have them in there to begin with, but I put them in there because it was either parentheses or absolute values, and it really didn't matter. But when push comes to shove, we can drop it, not because of the exponent, but because of the condition that was defined early on that says t has to be greater than 0. So it's establishing that t has to only be positive numbers. So once I come up with a natural log of t, as my antiderivative, well, I already know t has to be positive in the setup, so I don't need the absolute values anymore. All right. But what that's telling me to do is multiply everything by t cubed. All right. So I'm going to take that and multiply each term by t cubed. So t cubed y prime plus 3t squared y would be equal to t root 1 plus t squared. The left-hand side should be the expanded form of the product rule. Right? So if that's the case, then it must be the first function multiplied by the derivative of the second function. So this is the derivative of the second function. So that's going to be, that would normally be dy dt, but if I want the original expression that came prior to that, I would want just the y, because the second function must be y if this is the derivative of the second function. So once you make that claim or that decision, you would follow through with the product rule on this and say, okay, is this true? First times the derivative of the second. True. First, here's my second function. That's definitely the derivative of it. Plus the second function, yeah, times the derivative of the first. Derivative of t cubed is 3t squared. So this checks out. So this is an equivalent form, the product rule form. All right. The benefit of doing that is in the next step. All right. So I can move the dt to the other side just through multiplication. So d this would be equal to t root 1 plus t squared dt. Integrate. Left-hand side is just t cubed y, because a derivative and an integral cancel each other out. So then on the right-hand side, this is what I was talking about before, where it's saying, is there going to be a question that is directly in substitution? No, but it can work its way into the problem. Right? So this guy over here, you can probably do it with a little guess and check, a little u sub on the fly, but doing the u sub, I mean, final exam, so do the u sub out, for crying out loud, you know? So let the u be equal to 1 plus t squared, which would make du equal to 2t dt. All right. Looking at that integral, I see that I don't need 2t. I just need a t. 1/2, yeah. All right, so now I can pull out the t dt, replace that with just a 1/2 du. Instead of having the radical funny business here, I have radical u. But I'm going to write that as u to the 1/2. And slap my integral symbol around it. It's an indefinite integral, so I don't have to worry about bounds or anything like that. All right, increase the exponent by 1. Divide by the new exponent, which is the same as multiplying by 2/3. So you get 1/3 u to the 3/2, which would become, if we're reverse substituting, since u is 1 plus t squared, 1/3 1 plus t squared, with the left-hand side being t cubed times y. That's a poor quality too, so let me just fix that right quick. We'll do the plus c right at the very end. Before I do that, I want to divide both sides by t cubed to get y alone. So we get y equals, I'm going to write it as 1 over 3t cubed times 1 plus t squared to the 3 halves plus c. And that's a poor quality 3, so I'm just going to fix it up. All right. But you can see, I mean, it's a good problem if you want to get practice with a bunch of different calculus skills. Just not always the kind of thing you look forward to on an exam, but it's from here on out that that ideal linear differential equation, that scary concept. What is this? That's gone. From here down, this is all just U substitution, or whatever the type of function it is related to. It could be integration by parts. It could be partial fractions. It could be anything. I'm not evil, so I'm not going to tell you that there's going to be a standalone question on partial fractions, a standalone question on integration by parts, and then give you a question that has partial fractions integration by parts in it. All right, so those are standalone questions for a reason, because all the other types of questions will not involve those concepts. All right, so that's something you can kind of look forward to. All right, I'll come back to that if you're still writing. But I wanted to get a derivative or integral using a Taylor series real quick. Again, I keep saying real quick, but I'm not going to do it real quick. I think that was Christian. I don't want to rob you of the joy of doing one review. Have it on your own. So let me just snag one from the internet. Question. What we're looking to do. It's like I think it was the last question on the take home. So the idea is for you to come up with some summation or in a series that represents the antiderivative of this function. All right. So what we need to do is come up with that function. I mean, the rules are easy enough to work off. The issue is if I'm dealing with something that's not as nice as like the problem in the take-home test, where in this case, if I were to find the antiderivative, there's a product in here. That product is going to make things infinitely more complicated. It's not always as simple as just looking at it and saying, well, I'll just do reverse power rule. So sometimes it is, but sometimes it isn't. Right? So what we're going to do is focus on the Taylor series for sine of x. And, the rule is wonderful, x to the 2n plus 1, all that good stuff, but that's not the end of, the end all. What we need to do is come up with a relationship, and that relationship comes with kind of getting, sinking your teeth into the series itself. So I'm going to write out a few terms of it. And then I'll end up with the actual relationship, which is -1 to the nth times x to the 2n plus 1 over 2n plus 1 factorial. All right, so that's just rewriting the Taylor series for sine of x. All right. What I need though is x squared times sine of x squared. All right, so not the same thing. But one of our properties, one of our rules tells us that we can just substitute into the sine of x. So take the sine, instead of x, make it the sine of x squared. All right. The idea being that, yes, I can manipulate the final expression. Can I replace this with an extra? Sure. But maybe I can see the pattern or even a simpler pattern in my expansion just by looking at what happens if I plug it in for the first few terms. So it's kind of like you're reinventing the wheel a little bit, but for a purpose of making your life a little easier. Potentially. Doesn't always play out. All right. So if I were to plug it into the whole shebang, it would be -1 to the nth. Then instead of x to the 2n plus 1, it would be x squared to the 2n plus 1. We don't want to leave it like that, definitely. But I don't know that we want to simplify it just yet either. Because I don't just need sine of x squared, I need x squared sine of x squared. So it's multiplied through with an x squared. All right, so everything gets multiplied by x squared. All the way through. All right, so x squared sine of x squared would be x to the 4th minus the x to the, I think it would be x to the 8th. Because the 2 times 3 will give you a 6, and then you're adding another 2. So x to the 8th. Then x to the 12th. X to the 16th, yeah. And so on. All right. So we could kind of work it from both ends. But what I'm getting out of this is my denominator is not changing. The signage is not changing. So it's still alternating in the same progression, starting positive and going negative and so on. So this stuff can all remain the same. All right, the -1 to the nth. I can leave that as is. The 2n plus 1 factorial. The only thing that would remain is really addressing what's going on with the exponents. All right, I can do that one of two ways. One way would be actually to clean up this exponent, see what's going on. The other way would be to reason it out and say, okay, well, it's multiples of 4. All right, so wouldn't it be some kind of 4n, perhaps? I mean, if we're starting off with an n value of 0, I guess that doesn't make sense because we still need to have that. But if you had something like 4n plus 4, that should do it. All right? So there's some things that you can do in that regard. However, you could also get it just by simplifying. Because if I multiply these two things, I get 4n plus 2. And then I'm adding on another couple of powers, right? So keep the base, add your exponents. 4n plus 2 plus another 2 would give us 4n plus 4. So this becomes x to the 4n plus 4. All right.
Wouldn't the 4n become 8 to the n plus 4? Because you're adding, like you said, over 2.
Would it become, say again?
Where you have 4n plus 4. Wouldn't you have also added 2 to that?
Oh, no, I did. So I have the 4n plus 2 from this, and then I add 2 to that for this guy. So these two together become this.
Yeah, so wouldn't it be 6n plus 4?
You're only adding the 2 to the constant.
Or not the coefficient?
Not the end term. All right. So the benefit, I mean, you might look at this. I looked at it when I was a student. It's like, all right, this is something else. Like, You're telling me that this is somehow useful? And the answer was yes, because of what we're about to do. So we have all of this stuff here, and let me just kind of really make it look, or at least as nice as I can make it look. Which takes a while sometimes. All right, so we have all that stuff multiplied by x to the 4n plus 4. All right, what we have is a power relation, or power expression, power function, power rule. All right, so if I'm taking the derivative or the antiderivative of this, all I have to use is the power rule. Because anything that comes out of this ugly fraction, this nasty ass fraction here, anything that comes out of this, whatever it is, it's going to be a number. Whatever comes out of this expression here, it's going to be a number. All right, so we just took something that would involve integration by parts to come up with a solution. And I don't even know if that would work because I haven't considered it. But we took something that was integration by parts and made it into something that would just be simple power rule. All right. So increase your exponent by 1 because we're looking for antiderivative. All right. So this is my f of x. So what I want is f of x as a capital. That's the notation for the antiderivative of your lowercase function f of x. Because the last thing I think you want to do is slap an integral symbol around this thing and try to make sense of it. Alright, so I'm going to increase my exponent by 1. Alright, so new summation based off of the old summation. So all that good stuff, that's still going to be there. I'm going to have negative 1 to the nth. I'm going to have my 2n plus 1 factorial. I'm going to increase my exponent by 1, so 4n plus 5. And then divide by that new exponent. Plus c. Okay, so this expression, whatever it equates to in the form of a function, would represent the antiderivative of x squared sine of x squared. Alright, so we don't actually have to identify what the function is equivalent to. If you look at that and say, oh, that's clearly an equivalent to e to the x, or ln of x squared minus 4, okay, something like that, where you just happen to know the Taylor polynomial that equates to this, then by all means, you can write it, but it's not the easiest thing in the world to find. I mean, we had it for that today, but we're also figuring cases pretty good. Okay, so you're following a progression. I mean, you could conceivably just work off of the rule, but I like the expansion, feeling it out, multiplying, substituting, and things like that, because everything seems to make more sense when you do it that way. And then, oftentimes, you don't even have to operate with this, because you say, all right, well, these are clearly multiples of 4, so what kind of expression can I write that would allow me to start with an n value of 0 and allow all of these exponents to be multiples of 4? You know, so you get it one way or the other. One way is almost completely rule-based and procedural. The other way actually involves a little bit of, you know, understanding. And, you know, obviously that's the one I like.
So you have